So good morning, everyone. My name is Saining, and today I'm going to talk about deep representation learning with induced structural priors. Just a little bit of myself. I'm a Ph.D. student at UCSD. I'm working with Professor Zhou too. And during my Ph.D. study, I have spent time in different industrial research labs. But this is my first time at AI2, so I'm super excited to present you more about my Ph.D. work. Okay, so to begin with, I want to briefly just revisit the traditional machine learning flow. So you're given some input, right? And it's typically from a specialized task. And there should be like a human in the loop to do so-called feature engineering work. And then like you have a classifier and you get a output from the classifier. This is the traditional machine learning flow. And the promise of deep learning is that we do not really need to do this heavy feature engineering anymore, right? So the feature extraction and classification can be automatically done using a neural network in an end-to-end manner. But we all know like this is not the case, at least for now, because for real deep learning flow right now, it's like we have some input, there still will be some human in the loop. Instead of doing this heavy feature engineering, the human is actually working on the architectures. Okay, so we definitely don't want to kind of fall back to the feature engineering era. We need tons of like domain knowledge, handcrafted features, but it seems like a little bit long way to go towards the final ultimate goal of universal and this kind of general artificial intelligence. So what do? I think my perspective is like we should really apply this Occam's razor here. We want to find the minimal and transparent structural priors that can provide maximal flexibility. This is really important because if you're designing an architecture, you want your architecture that can be kind of generalized to different tasks or even different domains instead of like just doing one specialized task at a time. Okay, so let me give you a very good example of what a good structural prior is. So everybody knows like, oh, MLP is a universal function approximator, but there's not too much structural priors built into MLP. And by designing the convolutional neural networks, there's one really important structural prior that is incorporated into this kind of design decisions, which we all know is the translation invariance implemented by the weight sharing mechanism, right? And by having this translation invariance structural prior, actually we can learn, for example, to recognize the image much more effectively. And most importantly, this translation invariance structural prior can be generalized to different domains as well. That's why we all say that convolutional neural networks has been applied to different tasks as well, including like natural language processing tasks. Okay, so this is the outline of my talk today. I'll mainly cover 3 papers. And the central theme of all those papers is like how we can really incorporate useful, minimal, and transparent structural priors into building like a neural network architecture that can be generalized well. All right, let's jump into the first part. I'm going to talk about like holistic nested edge detection, or simply HED. This is a word in collaboration with my advisor Zhou too, and we are fortunate enough to receive Multiprize Honorable Mention Award in 2015. Okay, so what is edge detection task? If you're not familiar with that, it's really simple. You are given an original image. It's typically just a natural image, for example, a cat on the grass, something like that. And you want the machine to predict the edge map of the scene in the image. Okay, so this will be kind of the desired output of the edge detection system. So to start, I want to show you briefly about the history of edge detection, which has been more than 30 years. So I think because like the edges, the perception of the edges is actually primitive in our human perception. So people are studying edge detection long time ago from a psychophysics or even cognitive science perspective, including David Marr's early work. And then people are using computational methods in statistical signal processing to really develop these edge detection tools, such as the Canny edge detector, which you probably will learn in every computer vision textbook. Then Jitendra Malik's group at UC Berkeley made a kind of a great contribution to this field by proposing this Berkeley segmentation dataset and benchmark of BSDS. And they proposed this kind of learning-based methods based on carefully designed features. And then more machine learning techniques come in, and there are like a lot of new techniques, such as the Bell and using structural forwards to do the edge prediction tasks. And then we are coming to the deep learning era. There comes to our work HED. All right, so let's take a closer look at the BSDS dataset here. So for every image is actually labeled by multiple human subjects. And what's interesting here is the annotation instruction is actually deliberately weak, such as dividing the image into some number of segments, and segments represent things or part of things, and all of the segments have approximately equal importance, something like that. This is really weak, okay? So this tells us, like, this is not really a signal processing problem. You cannot really do this just by looking at the gradients of your image. So this is actually a cognition, artificial intelligence task, because it involves some high-level semantics, some high-level image parsing that is like really our human beings can do really well. And this is some like annotation results. So human visual perceptions are extremely consistent and diverse. And this is like the ground truth of this data set. Yes?
How do you define the ground truth for edge detection? For example, why there is no edge around the eye? So
Yeah. So that's a great question. First of all, like the edge detection task is kind of an ill-posed problem, right? There's no like well-defined edges. You cannot really define what is an edge mathematically. That's why like the Berkeley segmentation dataset is really important here, because all the ground truths are labeled by multiple subjects, and all the ground truths are just purely based on kind of the lab environment, what a human will perceive at that edge. Okay, so yeah, we really don't really tell about like why, but of course it makes sense if you look at the annotation instructions, right? Because you're asking why the eyes is not like the edge points there, and even like in the cat's body, there's a lot of fun, detailed textures, which is not categorized as edge points. But this is also consistent with like our human perceptions, right? We don't perceive that as like object boundaries. They are just the two fun details. Yeah. Okay, so the perspective we are taking here on the main focus of the holistic nested edge detection work here is how we can really make neural networks scale aware. So why multiscale is really important in edges. So actually people studying this like from neuroscience, cognitive science perspective, and it has been proved like multiscale is really important. For example, like in the traditional Canny edge detector, in the Gaussian filter step, there's a hyperparameter sigma here, where you can actually control the scales of your edges. Right? If you have like small sigma, then you get like this kind of really fine edges. If you have large sigma, you get coarse boundaries. And as you can see, like if you combine those kind of multi-scale edge maps from a Canny edge detector together, the results is still not satisfying. This is far from the ground truth of the human labeling, right? So this is like how kind of a more modern machine learning-based edge detector works. So it usually adopts a sliding window approach, where you make this kind of patch to pixel or the pixel or the patch to patch predictions. So basically, if we want to incorporate the multi-scale processing ability into this kind of system, what people will do is to have this external image pyramid, which means like you will do multiple pass during inference by taking into like multiple images in different scales. As you can imagine, this actually slows down your whole processing speed by a lot. Okay, here are some like previous results on the BSDS benchmark. Although like deep learning, even back to that time, has been conquering many different domains in all different applications in computer vision, but unfortunately, edge detection is not one of them. So as you can see that the deep learning-based edge detector, this deep contour, is only 1% better than the previous best like non-deep learning method structured for forest, while being extremely slow because you have to do this like do the patch-based sliding window approach on this really large, for example, AlexNet networks. So it's really, really slow. Okay, so here are some key observations for this task. The first one is like for edge detection task. Actually, the fine scale and core scale are all important. Okay, we all know like in convolutional neural network, for the first convolutional layers, actually detect this kind of gobble-like edge detectors, and it might not be really useful if you are working on sort of like a high-level task. For example, image recognition is not directly applicable, right? If you have this kind of a low-level edge detectors. But because we are working on these edge detection tasks, so even starting from the first layer, the neural network output of the edge detector can be really, really useful. The second thing, which is more important, is like there is a natural pyramid in our convolutional neural network. This is due to the spatial downsampling, right? Because we have different receptive field size, we have different input plane size. So basically, we have a natural pyramid there. So ideally, instead of having a single scale input output, actually we can have like multi-scale outputs in just one pass. So how do we do that? Let's first just revisit some existing multi-scale network architectures. Of course, what you can do is something like a network structure like in figure A. You can have like network in different depth. Then basically you can concatenate the final results together because they have different layers. Then basically they are handling multiple scales. You can merge them together. Or you can have this kind of skip layer structures. You can just pull up the feature vectors from your low-level network and just concat them in the final layers. Or you can have a single model, but you can run it on multiple inputs. This is more like the traditional methods. And or like this is kind of the extreme case, you can actually do this separate training. You can train multiple networks. And they can have like the same input size, but you have like different depth of your network. So you have different downsampling rate of your network. And then you probably can ensemble those networks together. Okay, so here is our proposed holistic nested network. So basically the major difference compared to the previous ones is like for holistic nested networks, we actually have multiple side outputs. Each of the side outputs is actually associated with a specific loss. Okay, so because we are doing this, this is still one single model, and it's still just one single scale input, but you can actually get multiple scale outputs just at one pass. Okay, you can think like this is just a kind of an optimized version of the extreme case network architecture D, where you just kind of shrink and combine those different models into just one single model. Instead of training them independently, you just handle them with multiple backpropagation paths. Okay, so this is like more details of how we can train this HED system. As I said, like there will be some side supervision, side losses, and there will be a final fusion loss at the end. Okay, so everything, every loss actually just trained jointly. This is really favorable because we are actually learning to combine those multiple skills as well. Right? Comparing to the previous methods, people are just doing like simple averaging. Now we can actually train the system together and learn how to combine them. Another critical problem here is like 90% of the pixels here are actually non-edge in an image, right? So we have to design a strategy to balance the class distribution. Instead of like in traditional machine learning methods, people usually achieve this goal by sampling the patches, negative patches and positive patches. We can just simply reweight the cross-entropy loss by a hyperparameter beta, which is the ratio of negatives in the current batch. Okay, so there might be a question because we have like multiple site outputs and we have multiple supervision signals. One question is like, do we really need multi-scale ground truth, right? But the answer is like there's no multi-scale ground truth because like for human beings they don't label it. But the good thing is like we don't really need it. So what we proposed is like we can use something called consensus ground truth label. So basically, instead of having, because the edge maps are labeled by multiple subjects, we'll only treat just the one single point as a positive edge point if more than 3 subjects are labeling it as a positive. So you will see like an edge map like this. It seems like a little bit weird because you're losing a lot of information there, but actually it works pretty well. And this is some like prediction results. You can see like even though like for consensus edges, they fail to really capture these fine details in the ground truth, but actually during the prediction you can learn it and can reconstruct it. This is just because like those kind of consensus labeling are just some essential edges. This actually solves the problem because we don't have the multi-scale ground truth, but if you have the consensus labeling, we actually don't need that. Okay, so here are some like illustrations showing the multi-scale site outputs really work. So on the first row of each image is actually with the site supervision. Okay, as you can see that like from the lower layer of the network, from the kind of the first set outputs to the higher level of the network to the final set output, the edge prediction results are becoming increasingly and progressively coarse, right? But all the kind of important edges are preserved in every stage of your prediction. But if you remove the site supervision, actually you can see results are kind of lack this discernible orders, right? And a lot of like structures, edges are actually lost, especially in the final stage of the edge prediction. Okay, because we have a fusion loss as well, so what we can do is we can also combine the multiple scales into one final prediction results. So here shows like the different scales of our edge detectors, right? And by kind of learning to combine them together, we can get something that is much better than a Canny edge detector and is sort of like close to our human perception. Okay, again, these are like the previous methods and what they can achieve on this BSDS datasets. And here comes HED. As you can see, by incorporating those really kind of strong multi-scale priors into our neural network architecture design, we can dramatically improve the results, and it's kind of approaching the human performance as well. One thing I want to say here is like human perception is really diverse. This kind of green dots there is actually a kind of a agreement between multiple subjects, and those kind of black dots there is actually from multiple subjects. So we are approaching this kind of green dots there. Can we claim that we are solving human perception? We cannot really make this kind of claim. There's a lot of work to do to really kind of approaching the human performance, even on these kind of low-level tasks. Okay, this shows like because we're using deep learning architecture, it's really flexible to extend to different data modality. We can process the RGB-D data as well. Everything is pretty much similar, and we can achieve much better performance. Here are some qualitative results of our edge detection system. And here are more. Okay, so after HED, I think it has been widely used edge detectors for many tasks. Yes, please.
Do you have any results comparing with other multi-scaling approaches?
Yes, we have something in the paper, but I think it's really hard to compare them like qualitatively. But basically, the results number here, this number structure edge is actually after combining multiple scales. Okay.
Which one?
This one. And also this one, all the deep learning based models, why they are so slow, one reason is because they are running this kind of on multiscale inputs. Yeah, so basically most of the methods here are already considering the multiscale. Yeah, so it has been widely used edge detector in the world, and it has been used, you probably see that like in image-to-image translation tasks. And also like the exactly form of the holistic nested networks has been adopted in many low-level vision tasks. Okay, for example, like in medical imaging or in silencing prediction, in skeleton extraction, because they share some similar property as the task of edge detection. So the exact form of this network structure can be used there. Okay, and this just to kind of summarize, like the multi-scale prior actually has become more and more important in like current computer vision systems, even in many high-level computer vision tasks, including post-estimation, segmentation tasks, object detection tasks. Okay, so that concludes the first part. Any questions? Okay, so maybe we can move to the second part. In second part, I'm going to talk about like my work with Facebook AI research, and this is called ResNext, aggregated residual transformations. Okay, so the task we are working on here is image classification, but we all know like nowadays working image classification does not really mean we are working for the image classification tasks, right? So the most important thing we want to get from this image classification networks is we want to build backbone feature extractors that can be generalized well in all kinds of different other applications. Okay, so the main focus of our work here is how we can really build a structured sparse neural network. Okay. Why structured sparsity? So like my friends in neuroscience tell me this is probably the most influential paper in neuroscience in studying this kind of complex human brain networks in recent decade. And one of the most important observation there is actually in our human brain, actually the connections are in a small world structure, which is actually structured sparse. Okay, so I want to just revisit some of the classic convolutional neural network. So there's a small thing in the original Lynette paper. I don't think like a lot of people will remember this. So the connection between the S2 and the C3 channels are actually sparse. They are not actually densely connected, they are actually sparse. So this is achieved by a sort of a handcrafted binary pattern showing on the right. Let me explain. So where the rows here and the columns here are different channels from those kind of two layers. Okay, so if there's a cross there, it means like there will be a connection between channels. Okay, if there's like blank, there's no connection at all. So this is really like a sparse connectivity pattern there, but it is handcrafted by Yan and call this. Okay, so why do they do this? I'm just gonna quote one sentence in the paper. So what they want to do is like they want different feature maps are forced to extract different, hopefully complementary features because they get different sets of inputs. Okay, although like this makes great sense, but there's not really kind of analysis or even results to prove this. But it's there, the sparse connected pattern. Okay, then let's fast forward to AlexNet. So AlexNet has a specialized thing called grouped convolution, which means like you split input and output channels by half if you have two groups. if we, again, represent it in the same matrix, like as in the Lynette paper, we will say like this is also about like sparse connection between channels, right? If you have two groups, this basically means like you have like the connections like this. Okay. Although like this was purely an engineering compromise back to that time because LS cannot fit the whole network into just one GPU, so he had to kind of split the network into two GPUs and then train the whole system. Okay. But it kind of accidentally confirms Yan's paper's hypothesis. So on the right are the kind of future visualizations of the first convolution layer. And with this kind of a group convolution training in the AlexNet, this is very surprising, like a disentangled representation naturally emerged. Okay, so one group here kind of just to learn the edge filters, gobble-like edge filters. And another group actually learns these color blobs. And this is naturally, there's no any constraint, this is just naturally learned just because you are turning that in two different groups. But comparing to like a ZeroNet, where there's no group convolution, you can see like those kind of edge detectors and the color blob detectors actually randomly interleaved. There's no like clear pattern of separation here. Okay. Okay, so instead of having like just the two branches in AlexNet, GoogleNet on Inception networks, they use a template module to do this kind of multi-branching. Usually there will be 4 branches, right? So the template is kind of a highly engineered, I would say. They are really heterogeneous. And I mean, GoogleNet is no doubt an excellent recipe. There's a lot of cool ideas there. But one of the problems is like this kind of a heavily engineered architectures sometimes can be really hard to generalize. Okay. So here is ResNext. So what we are aiming to do is to develop a principled approach to achieve this kind of a structured sparsity. One direct way to do this is to kind of adopt this multi-branching idea from the GoogleNet and add it to a kind of highly modularized ResNet network. Okay, so what we can do is like we can have like a uniform multi-branching instead of like the heterogeneous multi-branching GoogleNet, and we can build a network like this. Okay, so the ResNext, the next here doesn't just mean ResNet 3.0 or something like that. It really means like a next dimension in your network design. So previous like kind of a 2 dimensions people are working on to increase the capacity of a network. One is depth, right? And another one is width, which means like number of filter channels. And what we propose here is like there might be a 3rd dimension, we call it cardinality, which just means like how many paths, how many branches, or how many like this kind of a transformations are in each of the your kind of a modularized template. Okay. So one thing I want to mention is like because we are having this uniform multi-branching, so basically this kind of a next dimension cardinality will be a factor that can be isolated and studied. Okay. So you can freely tune this kind of cardinality numbers, and you can see the trade-off between depth and width and cardinality. So it's a good thing to have uniform multi-branching here. But if you think about it, to really implement this, we need to be smart in implementation. So it's probably really easy if you want to have a 2-branch system. It's trivial, right? But what if you want 32 branches? As I said, like this kind of a cardinality is actually something we want to isolate and study. So basically, we probably need 32 paths or even 64 paths, right? And then basically, the memory and computation overhead is huge. Basically, you cannot really make it work if you just brute forcefully increase the branches. But one thing that is interesting is like you can find out like this kind of multi-branching can be summarized into just a really succinct form like B and C. So for A to B, this really means like you want to what you can do is you can concatenate the output and you can have like a wider network at the final layer, and this is like totally equivalent to the previous multi-branch system. And from B to C is more interesting because like we find out that in a specific like ResNet template where you have 3 layers here, actually this kind of a form B multi-branching system can be directly implemented by an existing group convolution module here. So instead of like having like this real multi-branches, okay, what you can do is you can have multiple groups. And this is exactly the same group convolution in the original A-SCN. Okay, but as I just mentioned, like the group convolution in A-SCN was just an engineering compromise, and is actually being discarded from the mainstream development in different like platforms. But we find something new about like this group convolution here. Okay, so if we again represent it in the original Lynette matrix, what we can observe is like for ResNext, what we'll achieve here is a principal structure sparsity pattern where it's just a block diagonal matrix, right? And the sparseness is actually controlled by 2 factors, the cardinality and also like the individual dimension within each of the group. This is really flexible because, for example, depth-wise convolutional exception is just one special case of ResNext. For depth-wise convolution, it's basically a strict diagonal matrix instead of a block diagonal matrix. Okay, here are some results. So on CFAR datasets, what we want to show here is like increasing the cardinality is an efficient way to increase network capacity. These 2 lines here, one the blue curve and the red curve, shows like the choices between increasing the width of your network or increasing cardinality of your network. As you can see, like under the same amount of computation, increasing the cardinality is always better than just increasing the width of your network. Okay, this means like we're learning better representations and we can utilize the parameters much more efficient.
Also the same comparison in depth.
For depth?
Yeah, meaning that
yeah.
you can use ResNext 29 or ResNet.
Yeah, exactly. So we showed that actually for this on this ImageNet experiments because it's more easier, right? What we get here, it's not like showing in this figure, but the general conclusion is if you have the same flops, basically you get better performance. If you have same performance, you get less flops. So to answer your question, one ResNext 50 model achieved the similar performance to ResNet 101, basically. So it's like a double computation compared to that. And the conclusion also holds on even larger datasets. For example, this ImageNet 5K dataset, okay? And we can see actually bigger margin. This really means like the larger dataset you have, basically you can learn better representation, okay? And after ResNext, there are a lot of like follow-up works. There's one recent one, like training ResNext on 3.5 billion images. This is a network they're using at Facebook. And what they are doing is like they're training ResNext on 3.5 billion images from Instagram and using this kind of pre-trained representation, pre-trained network to do the ImageNet classification tasks. And they can achieve like a much better benchmark results on ImageNet 1K. And people are developing the block sparse GPU kernel that's specialized to handle the sparse connection patterns. And also like ResNext perform well on 3D video classification tasks as well, so it can be extended to 3D. And also, as I said, like we're studying these image classification tasks, but the main focus here is we want to use that as a backbone architecture for like different vision tasks. So ResNext has been used as in all winning solutions in ImageNet and COCO computations last year. Okay, and here I want to show like this kind of a sparse connectivity prior can be really extended beyond just the channel-wise connections. Yes, please.
I just wondering, your ResNext 101, the group, so it was exactly the one that you showed. It was like 30
We show different comparisons. I can give you a rule of thumb. Is like we probably want to use 32 groups. This seems like to be a sweet point. You can push it to the extreme. For example, you can push it to depth-wise convolution, but the return is diminishing, and the computation is cost is higher.
So here, your ResNext 101 has the same amount of flops as the ResNet 101?
Yes, yes. So this is under this like two curves are under exactly same complexity. Yes, yes. Okay. Yeah. So basically, I myself I work a little bit on the video classification tasks as well with Google Research. So what we did there is actually proposing this network level and layer level sparse connectivity patterns, and I will skip the details. But the conclusion is like by combining this kind of network level sparsity and layer level sparsity, you can actually achieve a pretty good, like it can be fast and it can be accurate. It will be a pretty good choice to design a video classification network as well. Again, it shows like.
More about how you impose sparsity first.
Okay, yeah, sure. It's actually very simple. So you see in the network level sparsity here, so everything here is based on the 3D convolution for video processing, right? And as you all know, like the 3D convolutional networks are really heavily computational, like costly, and it's really hard to train 3D networks and overfits really easily. So one thing is like, one question you want to ask is, on a network level, do you really need 3D convolutions everywhere? Okay, do you need like 3D convolutions from your low-level network or to the high-level network? So the observation we found out is like, you actually don't need 3D convolutions in the bottom of your network. This is a little bit in contrary to our, I mean in low level. Okay, so what we use here is like we use 2D convolutions, which is sort of like on the temporal axis, it's sparse, right? And for the high level semantic layers, where you get sort of like semantic features, you apply these 3D convolutions to capture this temporal correspondence, and then it works much better. Okay, and it saves tons of computation because you have larger input plane in the bottom of your network. Okay, and for the layer level sparseness, this really means like to factorize the 3D convolutions into a 2D convolution, just handling the image plane, and following by a 1D convolution of the temporal axis. And this saves like a lot of parameter, so it's kind of a sparse factorized model, but actually it achieves exactly the same performance or even better performance than just the full 3D convolution. Yeah, so this is like the curve showing the results. As you can see, like combining these two things under the same amount of computation, you achieve much better results. Okay, next I want to move to the final part where I want to discuss this different task about point cloud recognition. Yeah, so this task is a little bit different than like the tasks I have shown you before about like this kind of image recognition tasks. So for point cloud recognition tasks, what we're trying to do here is to recognizing objects in a set. So for like traditional images, the pixels actually lie in a fixed regular grid, right? So you can apply this convolutional kernels on these kind of image planes. But what if you have this kind of set here, and you are really not paying attention to the orders of each of the elements? So what kind of operation shall we use? So the approach we are taking here, or the kind of the central question we're asking here is, how can we represent sets, and how can we model this contextual shape information? Okay, I want to first revisit a little bit about the traditional shape context descriptor. So basically, it's really simple, okay? And the task is like you want to find like the correspondence between two shapes in 2D. And what you can do is you can, first, you can sample some contour points on your shape, right? So you will have these kind of sample points. And then you can create this kind of shape context kernel, which is going to log uniformly distributed partitioning of the neighboring space. okay? And for reference points, what you can do is you can count how many points of your neighbor points that fall into different bins of this kind of a partitioning of space. And then you can build a histogram, okay? And this histogram can be served as a really good and rich description of the local shape there, okay? So the core idea here is distribution of the relative positions is a really rich description of the shape. All right, so we can easily extend the classic shape context into a deep neural network by just computing the affinity matrix here, right? All the kind of the assignment function, and we can compute this online for each of the point cloud. And the histogram here is actually replaced by a simple sum pooling layer, and we can also add additional transformation layer to project the features learned from this kind of histogram or pooled features into higher dimensional space. Then we can stack those blocks together one by one to form deep network. By using this shape context, we can propagate the contextual shape information throughout the network and in kind of a hierarchical fashion.
Question?
Yes?
Could you just do like 3D convolutions?
Yes, so basically we can't for the point cloud representation itself, but we can do that on the voxel data, which is sort of rendered from the point cloud data. And people are kind of avoiding the 3D convolutions because it's super expensive to even do the voxelization there. So kind of the point cloud is more like a raw input, and what we want to do is kind of build network structures that can directly handle this specific data type. Yeah. Okay. Yes.
So then the order of points would matter here, yeah? Because if you order the points randomly each time, the output of each filter would be different.
Actually, does not matter because yeah, probably you can look at the details of our paper, but the core idea here is what we are doing here is for each of the reference points, we're computing these kind of kernels, right? And it's just the relative context information within just that reference points. And we are doing this for all the points in the point cloud. Okay, so in fact, what is that? We are not doing the max pooling at all. Yeah. If there's max pooling, of course, it breaks the order invariance. Yeah, that's a good point. So here are some results. As a toy example in 2D, as you can see, we have a curve like this. This means this shows what we are trying to do by building this kind of deep neural network architecture. So 1 point here, the 1.18% error rate, this is comparable to traditional machine learning baselines, right? So you first have a shape context local descriptor, and then you add an MLP layer there, okay? And by just stacking multiple these shape context kernels to form deep neural network, you can achieve a much better results, yeah, by going just deeper and deeper. And also, you can do this for 3D point clouds easily. And as you can see, by choosing a specific hyperparameters and carefully design this shape context kernel, you can handle the 3D point classification tasks in comparing to previous baseline methods, PointNet, which did not really consider the contextual information within the neighboring points. We can achieve much better results. Okay, but here's one problem. I'm saying we want to moving forward, and we do not want to fall back to the traditional feature engineering thing, right? So what we are doing here is actually doing the feature engineering, right? Because we have to design the shape context kernel for every data you have. Because for different data type, different data set of a point cloud, it can be of different density, it can be of different distribution, something like that. You probably need to tune all those kind of parameters of your shape context kernel one by one for your data sets. So this is really not what we want. But we can borrow something from natural language processing. This is, I think many of you are really familiar with this work from Google, self-attention So basically, self-attention is kind of a non-local transformation, and it's really kind of efficient to learn this distribution over relative positions by just learning some feature vectors and do a dot product by this kind of equation here. So instead of having to design all those ShapeContext kernels, what we can do is we can replace this ShapeContext block by this self-attention block. Okay, so because it also captures this distribution over the relative positions, by using this using this self-attention block, we can actually automatic and dynamic to do this kind of feature selection or the partitioning or the aggregation step in the regional ShapeContextNet. Okay. So here are some visualization of what we learned from this self-attention module. As you can see, the network is really learning to attend to discriminative parts of the shape. Okay. And on the right, it shows the attention actually becomes increasingly sparse in just the focusing on really small, compact areas in your shape. Okay. So the resulting model is of similar performance to original ShapeContextNet, and there's no data dependent in hand-designed kernels, and it will be more efficient as well. Yes?
I don't get this, how does it work?
Yeah, there's some details I skipped. So basically, so I think the main thing about the ShapeContextNet is you have to compute this affinity matrix here, right? It's n by n by L. L means number of bins, n means number of points. This kind of affinity matrix is actually handcrafted by designing the ShapeContext kernel, right? And what we can do here is if you are using self-attention, you can in each of the block you can learn these feature vectors. Okay, these feature vectors are of n points and times a d, which is kind of the feature dimension of that specific feature vector. And when you do the dot product, what you get is actually an n by n feature transformation, which is the attention weights of your network, right? So this is similar to, so every dimension matches with the previous ShapeContextNet, but now there's no handcrafted bin assignment you have to compute based on the data.
Basically, you're training the parameters of your meaning.
Yes, you can. Yeah, in a way, you can think about that. So for the visualization, it's also it's easier to tell. So basically, there will be a reference points here, and for this reference points, you are learning the kind of a connection strength between some other neighboring points, and this is automatically learned. Okay, and
So it's like a learned affinity kernel.
yes, but it's achieved by the self-attention, which is super efficient. Yeah.
And then the accuracy was better than.
It's similar, at least on the model net 40 dataset, for just the one single object recognition task on one specialized one special point cloud data. Then basically it's a similar performance. It's just a minor difference. And the good thing is it's more efficient because you don't need to compute the shape context every time. Yeah.
But you still, after you have the parameters of the bins, you need to compute the shape context. Yeah.
You don't need to do that because you can just do a transformation. It will be just a matrix multiplication, right? You have an n by n weights. You have n by d inputs. You multiply them together, and then basically each automatically learns. Yeah. And by using these conventional methods, basically you can extend this to segmentation tasks as well for the point cloud. Okay, so here comes some future work. So basically we cover sparse-connectivity prior. One interesting thing I want to try to explore is this kind of disentangled representation naturally emerged from this sparse-connectivity patterns. But we want to push this to a semantic level, right? So we want to find, instead of just looking at the first layer visualization, can you do this on the top layers? Okay, if we can do this, we can actually find some interesting connections to the knowledge and language tasks. And Also, I want to say how we can really kind of move from 2D to 3D. 3D really means like on the temporal domain or on the kind of geometric 3D domain. Can we learn better representations on these different data modalities? And another thing I want to do is like to try this structural priors, by interacting with the environment. And what I'm interested in is like some hierarchical IO approach, a meta-learning approach with intrinsic reward, and maybe using vision as a structural primitives. I think some of them are actually covered by some of the work happening here, right? Like the interactive VQA tasks, something like that. And also like transfer learning tasks. If I have time, I can briefly tell you a little bit, just some initial attempts to achieve these tasks. So basically, if you are hierarchical reinforcement learning approach here, one good thing that I found extremely interesting compared to traditional supervised learning, just to do learning from the data, is actually it's real easy to inject some structural priors as subgoals. Okay, and those subgoals can be hardwired, even with some grounded like language instructions, or it can be learned directly from the environments. And this is super helpful if you want to do the transfer learning tasks. So for example, you are solving this kind of navigation tasks with an ant going across the walls. And what you want to do is like you want to train on a normal ant. And when the kind of low-level body changes, you're still working on the same environment, same task. You want to get better sample capacity because you want to get a better understanding of the environments by using some sort of intrinsic reward that is guided by some structural priors. So for example, this is just the very, very early attempts. By knowing that this agent is working on a 2D plane, and by giving the subgoals like moving forward for 1 meter, moving right for 1 meter, something like that, this kind of discrete instructions, we can actually do much better when we transfer to a different body. So this shows like when we train on a normal ant and we break the legs of the ant, and as you can see, like if we can reuse originally learned high-level understanding of the task, and during the kind of fine-tuning step, we do not have any like task rewards at all. Everything is trained with an intrinsic reward learned from the pre-trained task. Then basically, the agent can learn to achieve the task goal much faster comparing just the training from scratch. Okay, so basically today we cover topics like multiscale prior, we cover topics like sparse-connectivity prior, and we show some early attempts how we can learn the structural priors directly from data using attention mechanism or hierarchical IL. And I guess like there's a really interesting debate about like, the kind of nature versus nurture. So structural priors, we all know like they are necessary to achieve like reasonable sample capacity in basically every machine learning system nowadays, right? But it's also true that the more structures you have, the more chances they will be wrong. So we do not have like that much of a structure. So what we really want to do, at least this is my point of view, is we want to find those kind of transparent minimal primitives and scaffolding to help us to learn more effectively. Okay, so it concludes my talk, and I want to thank all my collaborators and mentors in my PhD study. Thank you so much.